in the morning, the talk by Francesco Buscemi has been cancelled. So I'd like to invite Kotaro Kato as the first speaker of this session. He's from the Graduate School of Informatics, Nagoya University. The title of his talk is Exact Renormalization Flow for Matrix Product Density Operators. So please start your talk.
Thank you for the introduction, and thank you for inviting me to this very diverse workshop. So today I'll talk about some, fundamental result on tensor networks, which is a way to represent many-body quantum state efficiently. So before going to the details, I just introduce what is a tensor networks. So tensor network is, as I said, represents efficiently representing many-body state or operators. So in usual quantum mechanics, many-body quantum state is written in this way, where I1 to In is just a tensor product of local Hilbert space, and Ci1 to In is a coefficient of the wave function. And usually this Ci1 to In, to specify the quantum state, we need to change each index from 1 to D, where D is dimension of local Hilbert space. So the number of coefficient is just D power N, and it is exponentially large with respect to N, number of spins or sites. However, in real physics, it is typically these wave functions can be represented in more efficient way, and you don't really need those exponential number of coefficients to specify one state. For example, in 1D case, usually people think matrix product state, which is graphically written in so this way. So this is one way to represent coefficient in terms of some tensors A to AN, and by decomposing this coefficients into small pieces, one can construct some efficient way to represent quantum states. Of course, this is, there are a bunch of different kind of physical systems. So we usually choose one proper networks of tensors to represent the state in that physical situations. For example, these top two, this matrix, so-called matrix product state representation, or this kind of 2D array of 2D lattice of small tensors used to describe wave functions in so-called gapped systems. I'll explain the definition later. And other example is so-called critical systems, where the gap is just closed and some critical phenomenon happens between phase transitions. Then the state have a more different kind of properties, universal properties. So it is better to use, for example, in 1D case, this kind of tensor networks called Mera. And moreover, in high energy physics, people studied, for example, holography principle, or black hole properties and microstate of black holes. Then people use this kind of hyperbolic geometry or consists of small tensors. Anyway, so this kind of representation, efficient representation of coefficient is very useful in numerically and analytically, and there are a bunch of various applications in quantum physics. So I'll explain more about this, what is this diagram really means. So there is in tensor networks, there is one rule. So this each circle or a square, this component represents a tensor, and they have a similar open legs. And each open leg corresponds to one index of the tensor. And when we specify every index, then we get one complex number. So diagrammatically, this is just a tensor with 3 legs, and we can change the value of A, B, I from 1 to D and 1 to D, large D. Or actually, these D can be different for each legs, but here we just consider when the size of A and B are the same. And in that case, if we fix I and regard this AB as the index of matrix, then this tensor is actually one corresponds to a matrix labeled by I. And this is a square matrix because we set this A and B are same size. Similarly, if you consider this kind of tensor B, this tensor has two legs, J and C. And if usually we regard this vertical legs as just index of some vector or matrices. In this case, B only has one horizontal leg, open leg, and this corresponds to the element of a vector. So this can be regarded as a vector labeled by J. And if we connect these open legs and make another tensor, connected tensor like this, then we take a rule that the index connecting these two tensors just summed up, meaning that if we consider this tensor, then this represents the tensor defined in this way, where B is summed up and just contracted. And actually, this is a multiplication of a matrix onto a vector. So according to this rule, matrix product state can be written in some diagrammatic matrix product states are example of tensor networks written in these diagrams. So these are states living in some, n-body quantum system. And this state is called matrix product state, or MPS in short. If this Ci1 to Cin can be written as a trace of product of matrices, that's why they named as matrix product states. And each matrix AI1 is just a D times D matrix, where dash D is some constant. And diagrammatically, this means that this C, which has I1 to N indices, can be decomposed into a bunch of product of matrices. And here we connect this left leg of A1 to right leg to AN because we are taking trace here. And this is MPS, and actually to represent MPS, the number of parameters needed to specify one MPS is just given by small d times large N, which is site number, times large D square. And this is polynomial of N and much smaller than the exponential number D power N, which is needed to represent general coefficients. So this is very restricted class of quantum many-body states, but useful in quantum many-body systems. And also another property, well-known property of matrix product states is these states always satisfies the so-called area law of entanglement, which means that if you consider some if we divide 1D system into two parts, X and complement, then calculate entanglement entropy between them, which is defined in this function, von Neumann entropy of reduced state. Then it is upper bounded by the size of the boundary region, which is in 1D case just log D or log D square. Constant anyway. So these are just formal definition of matrix product states. But what we are interested in is what are these states in some physical settings, and what kind of physical systems very well approximated or characterized by this kind of subclass of quantum many-body states. Those are actually 1D gapped systems. And so in physics, most of the systems we can describe by 1D local gapped Hamiltonian. And also, when there is frustration-free property, then the physics becomes much easy to understand. So frustration freeness, so Hamiltonian is given by some of HIs, small HIs, interaction terms. And frustration freeness meaning that the ground state of H is also ground state of small HI. When this condition holds, then the system is called frustration free. And local, Hamiltonian being local when each HI only acts on few neighboring spins or sites. And also, people call Hamiltonian is gapped, or the system is gapped when the spectrum, energy spectrum of the Hamiltonian is distributed in this way. Usually in finite systems, it is just discrete spectrums. But if we take n to infinity, so the system goes to infinitely large, and it is also called thermodynamic limit. If there is a gap between the lowest energy level and the first excited energy for any system size. So if this delta is constant for any n and remaining constant for any n, and survives at the thermodynamic limit, then the system is called gapped. And you can have some degenerated ground state, but the first excited state must be finitely away from the ground state in terms of energy. So this gapped condition is very strong and push lots of constraints in the actual phenomena happening in that kind of systems. And MPS is very good to describe that kind of ground state in gapped systems. So it is mathematically proven that MPS contains the gapped ground state. So in the sense that any 1D gapped ground state can be approximated by MPS, where the bond dimension D is actually not the actual constant, but can be chosen to be polynomial of n, which makes the MPS is still specified by polynomial number of complex numbers. And also, it is known that any MPS can be regarded as some ground state of some local gapped frustration-free ground states. And that kind of local gapped frustration-free Hamiltonian is called parent Hamiltonian. But anyway, so for a given MPS, one can always construct Hamiltonian such that the given MPS is a ground state of it. So in this sense, MPS and this gapped ground states are kind of equivalent. This is nice characterization of tensor networks in terms of physical concepts. So one nice thing for MPS by using MPS is that MPS has a very nice coarse-graining operation. Which is often called renormalization group transition or renormalization group flow. So renormalization is a process which coarse grains some, physical systems to get lead out some kind of universal property of the states or the phase of the system, irrelevant to some short-range physics happening in some, minor perturbation or something. So, and MPS, for any MPS defined in this way, one can always regard these two neighboring tensor as one huge tensor, like say AA. And by using some, conditions, we can always show that there exists some isometry from CD to CD tensor 2, such that the whole tensor AA is, actually decomposed to isometric part and some another tensor A tilde. And the important point is A tilde is now just, one site tensor, meaning that this physical leg is, reduced to CD, just a single site Hilbert space from this two sites Hilbert space by isometry. And the proof is very easy because we can always regard this whole tensor AA as a matrix, and you can just apply the polar decomposition to get this decomposition. So the V is the isometry from polar decomposition. This A tilde is just positive part of the polar decomposition. So by repeating this kind of denormalization flow, because this is always isometry, we can repeat many times and it is exactly reversible. And eventually one gets the RG fixed point. And this fixed point is very well characterized by isometric MPS, meaning that each tensor in the fixed point can be represented as some maximally entangled pairs, and applying some isometry between the pairs. And this characterization allows us to classify some, what are possible quantum gap phases in one-dimensional systems and so on. And in this talk, we are focusing on some generalization of MPS called matrix product density operators, MPDO in short, which are defined in this way. So the only difference is instead of one indexed matrices, we consider two indexed matrices. This tensor network state is a natural generalization of matrix product state to 1D mixed state. And actually, in lots of researches, these MPDOs are used as good answers for describing thermal states or a steady state in like dissipative dynamics. And actually, it is known that any given state of 1D local Hamiltonian can be approximated by MPDO, just like the case of MPS and gap to ground states. However, these MPDOs are more general than given states, and actually, it is strictly larger. So in 2D pure states case, people use PEPs, which is 2D variant of MPS, to describe the ground state. And if you consider PEPs on some open boundary condition and taking a trace, contraction about the bulk, meaning that these vertical legs, degrees of freedom, then what we get is some remaining degrees of freedom at the edge. So in this sense, people say that D-dimensional pure states have some D-1 dimensional mixed state boundary theory in tensor networks. And actually, these D-1 dimensional mixed states are typically in this 2D pure state case described by MPDOs. And if we in 2D pure states, there are some interesting physical systems called topological orders. And for example, the famous example is the toric code. And if we consider boundary theory of the toric code, what we get is some MPDO which is non-thermal. So the MPDO is just a tensor product of identity plus tensor product of power Z. This operator is global projector and cannot be written as some given state of local Hamiltonian. So the question is what kind of states this MPO can characterize. So it must be strictly larger than set of given states, but what is the limit of these MPDOs? That's the question. To study that kind of capability of MPDO, it would be nice to consider again denormalization fixed points and then just classify the fixed points. So in the case of MPDO, it is the MPDO is called a fixed point if there is a pair of CPTP maps. So in the previous case, that was isometry, but for mixed state, it must be CPTP map, such that mapping one tensor to two tensor and two tensor to one tensor. So the fixed point, it is fixed point. So denormalization is just, the renormalization map is described by map S. And because it is fixed points, you can always invert the renormalization procedure by another CPTP map T. And in terms of, equations, it can be written in this way, but intuitively it is just described before. And the nice theorem about this fixed point is that if rho is a fixed point MPDO, then rho is, intuitively saying global MPO times a commuting Gibbs state, which can be written in this way, where the first part corresponds to some, global matrix product operator part. And actually, the authors doesn't specify what kind of matrix product operator they are. But anyway, this is some kind of matrix product operator acting on the whole system. And the rest part is actually just a commuting Gibbs state. And the point is this commuting Gibbs state part commute with the matrix product operator part. So each PI just commute with every Hamiltonian interactions. However, so we have a nice fixed point characterization, but the problem is in this paper, they don't introduce the how to get to these fixed points from given MPDO, and it is not clear if there exists some sequence of CPTP maps which ended up in these fixed points from given general MPDO. So to finding that kind of renormalization flow is the main goal of this work. So the problem is finding, if we consider MPDO and divide the system into A and B in this way, finding CPTP map, which kind of denormalize or just, making small tensor from B and in a reversible way, so that we have some recovery operation from the compressed tensor to the original tensor by some another CPTP map. And we want to make this compression is converging in the sense that one can always make the size of B tilde to be constant, independent of the length of the B. Otherwise, you cannot, make renormalization converging. So this kind of problem is more generally called exact compression of bipartite state, quantum bipartite state. So which is for given some density matrix on bipartite systems, one applies some compression epsilon so that one can always recover the original state by another map D. So in this setting, the question is what is the minimal dimension of the compressed systems? It is actually given by the so-called minimal sufficient subalgebra. So this condition is well known. And it is characterized by some set of states generated from the original bipartite state. And the minimal dimension of the B is then derived from some algebra generated in this way, which is finite dimensional and C-star algebra. So general theory of C-star algebra says that there is always some decomposition of Hilbert space in this way, such that this finite dimensional C-star algebra is written as some matrix algebra on this block tensor some identity. And it is known that for any bipartite state, the algebra constructed in the previous way specifies what kind of dimension you obtain after compression. So for any bipartite state, the bipartite state can be decomposed in this way. This along to this decomposition of minimal sufficient subalgebra. And this decomposition is sometimes called Cauchy-Emoto decomposition, which decompose some correlation to quantum correlated part and classically correlated part. And you can discard this classically correlated part to get the minimal exact compression. So, okay, we know how to get the minimal dimension of the compression. So we want to apply this set property to MPDOs. So first finding of our paper is that unlike MPS case, for which every MPS has well-defined coarse graining operations, it is not so easy. So in the case of a mixed state, you have to again discard some entropies to keep the dimension constant. And that part is given by Kawashimoto decomposition. So this one can always discard this omega part to reduce the dimension, but sometimes it's impossible to get some constant dimension. So this is an example, explicit counterexample. So here we consider system of Q-treats, and this lambda is a 3x3 diagonal matrix where satisfying this kind of properties. But the important point is the eigenvalues of this lambda are different. Then, if you consider this kind of partition and check the minimal sufficient subalgebra, it is going to be algebra generated by identity tensor L and lambda tensor L. And this algebra is isomorphic to the number of eigenvalues of lambda tensor L, which is, if these eigenvalues are all different, then number of eigenvalues, distinct eigenvalues of the lambda tensor L is going to be polynomial. So it cannot be a constant. So in this case, exact RG flow must diverge. We thus consider a subclass of MPDOs to discuss exact RG flow. So in this paper, in this work, we introduce some two conditions to set this subclass. So the first condition is there are finite dimensional sister algebra such that, and some representation such that the minimal sufficient subalgebra must be some, isomorphic to the this algebra. So this guarantees that finiteness of the renormalization flow. Here, importantly, although this algebra is living in, very d power L dimensional Hilbert space, one can always decompose into small component, which is always constant dimension, and some large identity part growing with L. So only this part changes according to L, and this part is remaining constant. And this by this condition, there is a nice inclusion relation between minimal sufficient algebra. So if we further divide B into two parts with lengths L1 and L2, one can show that the minimal sufficient subalgebra of this B for B L1 plus L2 region can be a subalgebra of the tensor product of minimal sufficient subalgebra of smaller regions. So by using this inclusion relation, we have a nice map delta, which is diagrammatically written in this way. So first, we start from A, and the condition condition 1 guarantees that there is some, representation pi, which makes this minimal sufficient subalgebra is equivalent to pi L A. And this is because, subalgebra of this tensor product algebra. So we have some, inclusion relation. And then because this pi is injective, one can always invert this representation. And each of them, implies output is image is A. So in this way, we get some map from A to A tensor A. And we denote this map from A to A tensor A by delta. And the second condition we impose is the map we have just defined is independent of the choice of the L1 plus L1 and L2. This is kind of technical condition, but this induces very beautiful structure in data. because we can regard this map delta as a co-multiplication of algebra. So co-multiplication is some kind of opposite of multiplication and defined as a map satisfying this condition. So, after two multiplications, co-multiplications, the, either acting on left-hand side or right-hand side of tensor product doesn't matter. That's the condition for co-multiplication. So in addition to co-multiplication, we can show that actually A has a so-called co-unit, which is another kind of dual of unit in usual algebra. So co-unit is a map from A to C, the complex number, such that satisfying this kind of condition. So we can always back to the identity map from after applying co-multiplication. Yeah. So thanks to the existence of co-multiplication as co-unit, what we can say is the algebra we started is actually also has a so-called co-algebra structure, makes the algebra to be a pre-bi-algebra, which is some algebra and also co-algebra with some additional condition, which is clearly follows from the definition of delta in our setting. So because of the time restriction, we just skip the proof, but the sketch of the proof is, using the duality between co-unit of algebra and unit of the dual space, which becomes becomes algebra by co-multiplication. Yeah. Anyway, so we show that A is always become pre-bi algebra under our condition 1 and 2. And what we can show is that any MPDO satisfying the condition 1 and condition 2, there is some, representation pi L and by algebra A. And those MPDO can always be written in this way, where the first part is some kind of pi tensor L and delta and W. This part is some representation of by algebra. And there is some residual part, omega, and omega just commute with the MPO, this algebra part, representation part for any A. And omega is actually can be written in this way, and in diagrammatically, this is somehow, written as this kind of tree-like structure. But I omit the details and explain that, because that the previously we have shown, I introduced that there is some fixed point result, makes the state written in this way. And what omega, what pi correspond to in our setting is this representation part, and also what omega is that corresponds to is this commuting Gibbs state part, and we can directly show that this correspondence for a very easy example. So there's some, I prepared some few representation, proofs, but I just skip it. So basically, one can, the point is that one can always decompose the tensor according to this KI decomposition, Kowashi-Imoto decomposition. Then we can show that some, consistency condition between them to get this, structures. Yeah. Okay. So what we get is some, structure theorem for a state which admits some energy flow, and one can explicitly construct some renormalization map and inverse of that from the decomposition. So if we have some, if this tensor network MPDO has admit some converging energy flow, then it can be decomposed in this way, where this W is, matrix acting on physical subsystems. So this is acting on CD power, CD tensor L. And alpha beta is just, operator acting on these partial legs. And one can always decompose this W part to this sum of small matrix part and some huge matrix irrelevant part, just see before. And the renormalization operation maps this tensor to this new tensor, which is just taking trace over this huge part, huge omega part, irrelevant, correlation irrelevant part, and replace it by some small, correlation irrelevant part, omega A1. And we actually don't touch about this left-hand side part because, Kawashimoto theorem says that if you want to make CPTP map invertible, you shouldn't touch any of this element. And thanks to this, we can always construct some map, another CPTP map from this compressed tensor to this original large tensor. So this process is exactly reversible by CPTP maps. And finally, we see some, nice corollary or application of the structure theorem. So we have seen that exact RG flow implies some bi-algebra structure and some representation. And this kind of play-by-algebra stuff seems kind of weird because we don't see this play-by-algebra stuff in quantum information theory so often. But actually, this for a given play-by-algebra and injective representation, one can always construct the so-called MPO realization of algebra, which means that one can, represent this algebra by using some family of MPOs. So any element, for a given play-by algebra and injective representation, for any element of this play-by algebra can be written as some MPO by this, co-product and this co-multiplication and this injective representation. So the consequence is that if we consider the center of play-by algebra, then for any element in the center, then the MPDO, given MPDO with RG flow, must commute with the MPO realization of Z. So diagrammatically, this means that if rho has nice RG flow, then it must commute with this MPO algebra element. So this is a kind of symmetry, but now the symmetry action is not given by unitary on-site, representation of group, but some more general matrix representation of play-by algebra, which is not group. But this is kind of symmetry beyond group representation, now actively studied in physics. So that's all for my talk. And the summary is that we have studied some exact real space renormalization group process for MPDO. And we find that unlike MPS, MPDO does not always have some nice converging renormalization flow because the easy example shows that it must kind of diverge. And so we introduced some subclass of MPDOs with well-behaved RG flows and show that under that kind of conditions, one can derive explicit structure theorem for MPDOs, and we can say some, that kind of MPDO must obey some kind of symmetry described by MPO algebra. And the future direction is that, if we can relate this kind of play-by algebra stuff to 2D, boundary theory of 2D PEPs or topological orders. And actually, the symmetry of the boundary theory in this topological order stuff, 2D topological order, is given by MP algebra of weak hop algebra, which is a special case of play-by algebra. So I believe that this kind of, RG characterization containing the boundary theory of those, weird boundary theory of 2D systems. And also we are interested in, classifying 1D mixed states, connected by constant circuit, which is, recently actively studied in terms of mixed quantum phases. Anyway, that's all for my talk, and thank you for listening.
Thank you for the interesting talk. So now the section is open to the questions and comments. How about online participants? If no, I have a small, very general question about RG flow of matrix product states. I think usually the renormalization group is not reversible. I mean, since by coarse graining, we generally lose some information.
Yes.
So usually my impression is renormalization group is not reversible. But you said that in the case of matrix product states, it is reversible.
Yes.
What is the point compared with the general case?
So in the case, so why exact or reversible energy flow is important for MPS is because to characterize the phase, we need to connect these two ground states by a constant depth unitary circuit. So
the process is unitary.
Yeah, RG process corresponds to some unitary circuit. Then you can say that the starting point and the end point is in the same phase by definition. So it is one definition of gapped quantum phase. So two ground states are connected by such circuit. That's why reversibility is important. If we consider, of course, for numerical properties discussed, numerical approximations, then of course, we can approximate by insert some cutoffs and to see another physics. But to see gap, quantum phases, then reversibility is important.
I see.
And also, there are some examples of reversible renormalization for a classical case, because in classical, for example, Gibbs state of local Hamiltonian is a Markov chain, and you can construct exact coarse grainings for that kind of Markov chains.
I see. Thank you very much. Other questions? Comments?
So sorry, I could not understand the exact meaning. So you mentioned that Markov chain, but in the case of Markov chain, the definition is very difficult. How did you define Markov chain?
Oh, in my case, so classically, I'm considering spatial Markov chain or Markov network in more precise sense. So it is a probability distribution defined on a graph, in our case, 1D, 1D chain, such that the conditional mutual information between one region and, outside conditioned by neighbors is exactly 0. That's the condition for Markov network.
So you define Markov chain by using the condition for conditional mutual information equal to 0.
Yeah.
This is including a quantum case.
Yes.
Okay. In what case you can realize that kind of Markovian case in quantum? In classical case, we can easily find that case, but quantum case, it is not easy to find that case.
Indeed. So in quantum case, only commuting Gibbs state is example of exact Markov network, because there is some so-called quantum Hammersley-Clifford theorem. And for non-commuting Hamiltonian case, it is only called approximately, in the sense that conditional mutual information is not exactly 0, but small.
Thank you very much.
Other questions? If not, let's thank the speaker again. Thank you very much.
Thank you.
So the next talk begins in 5 minutes. 聞こえますか？聞こえますか？大丈夫ですか？はい。 Yes. Okay, let's resume the session. The second speaker is Teruaki Nagasawa from the Department of Mathematical Informatics, Nagoya University. The title of his talk is on the generic increase of observational entropy in isolated systems. So please start your talk.
Thank you for introduction. Today, I want to talk about on the generic increase of observational entropy. Thank you for introduction and invite me this workshop. Okay. Firstly, I want to talk about the introduction of our study. Firstly, in his book on the mathematical foundation of quantum theory, von Neumann introduced and offers an operational motivation or quantity that is now known as von Neumann entropy, or we and von Neumann also say microscopic entropy. However, he notes that this quantity is not the most appropriate to consider in the context of statistical mechanics. In order to address this challenge, von Neumann put forth the concept of macroscopic entropy, which consider not only the intrinsic uncertainty inherent to the microscopic state of the system, but also the supplementary uncertainty associated with the coarse grains and macroscopic observation with which the system is being monitored. Mathematical definition of this one. Von Neumann delivered first microentropy. Definition of microentropy is for quantum state law, S law is defined as minus stress law log law. And he also introduced macroentropy, which is different from microentropy. This generalization is observational entropy. Definition of observational entropy is as follows. For any POVM, fixed POVM and quantum state law, observational entropy defined as follows: minus sum over I trace pi rho log trace pi rho over trace pi is called observational entropy. This is image. Microentropy and macroentropy is long-lost brother. Von Neumann's original definition of macroentropy is limited to PBMs, this one. In order to show H theorem, proper definition of entropy, that is macroentropy is required. Our study aimed to recapture these arguments in modern way, especially using quantum information theory and observational entropy. Remark of H theorem. H theorem is entropy increase with time evolution, especially Boltzmann equation. Yeah. This is classical H theorem. And our study firstly defines macro states, and macro state is defined as for quantum state law and POVMP. If microstate and macrostate, microentropy and macroentropy, micro and macroentropy equal, then law is called macrostates. And the following inequality holds for observational entropy and von Neumann microentropy. This inequality holds. And for any P of MP and macro state law and unitary U, we have this inequality. This means that if we take macro states as the initial state, then observational entropy will increase with unitary time evolution with probability 1. This equality means that. And when does the observational entropy increase? In order to answer this question, we first need to provide a characterization of all macroscopic states associated with a given P of EMP. This is our first theorem. Given a P of EMP and state M is macro, given P of EMP, then state M is macroscopic state for P, if and only if there exists a PBM with satisfying this relation. This means that there exists a conditional probability distribution Py given X such that this. But in particular, PBM case, this conditional distribution is trivial. Then this means that PBM pi y is sum of the element of P of M px. Then macro state, if and only if this condition holds. This means that macro states is given by completely macro observer information. And this theorem means that in particular, if M is macro state for P of MP, then this relation is whole for all Px. And this fact demonstrates that the restricted set of unitary operation, that satisfies a conservation-like relation, this one can preserve the observer's information about the system. This means conversely, generic evolution such as one uniformly sample from the entire set of unitary operation will necessarily cause an increase in observational entropy. In such case, also the microscopic evolution is perfectly reversible, but from the macroscopic observer's perspective, information is irreversibly lost. And next, how does observational entropy behave when considering arbitrary quantum state as the initial state? Our second theorem, this one, theorem is theorem about our random case. Let us consider our d-dimensional system in arbitrary but fixed state row, and P of NP with finite number of outcomes and value row value delta. For unitary operator, you sampled at random according to the Hull distribution. Then the probability that the system's observational entropy SP U rho U dagger is delta far from the maximum value log D can be bounded as for this one, where KP is defined as minimum x trace px u. This is equal 1 over the minimum x vx. Vx is trace px. And C is defined, C is a constant. For asymptotically close sequence of, we consider asymptotically close sequence PD of P of M. That is such that this parameter satisfying this this relation. Then the right hand side of this one is of order D order this one. Then which goes to 0 for any delta in the limit of D goes to infinity. Therefore, for a system of sufficiently large dimension D, it holds that this one for any delta. We defined as a macro cos observable, cos P of M. Consider a sequence of system with increasing dimension D, and each system and P of M PD for each D define this parameter, and we say that the sequence of P of M's is asymptotically close whenever there exists delta such that this relation. That is whenever there exists capital M and natural number D0 such that this means that for cos measurements on a sufficiently large quantum system, then observational entropy observational entropy goes to maximal value with high probability. Similar results hold in more physically feasible pressed random setting. This means approximate to design setting. Approximate to design is defined as follow: fix delta and natural number T. Unitary ensemble E is epsilon approximate unitary T design in the diamond distance if this holds. Here METX is defined as follow, and MHTX is defined as and this form. Then our third main theorem of epsilon approximate unitary T design case, for unitary U sampled at random from epsilon approximate to design E, then we have this inequality. for any value delta. This means the upper bounds provided in epsilon approximate to design is less strength than that presented in the hard distribution. Yeah, this is due to the fact that the negative exponential rate in D, which was presented in the hard distribution, has been replaced by D log D, 1 over D log D. Our random case is this one, but the epsilon approximate case is replaced by this one. Now, in the case of epsilon approximate to designs, we require that this parameter is this form for some out. Therefore, for any sufficiently large D, even in the case where U is sampled from epsilon approximate to design, it still holds that for any delta, we have this condition. This means that the observational entropy is where certainty increase in the setting of epsilon approximate to design case. Okay. This is conclusion. This research presents 3 methods in which observational entropy is shown to increase and reach its maximal in isolated system undergoing generic unitary evolution. Firstly, if the initial state is a macro state, then observational entropy will increase with probability 1. And secondly, if we consider unitary time evolution in Hall random setting for arbitrary initial states, then we can show that it's increased with very high probability for coarse macro measurements on sufficiently large quantum system. And finally, it was found that observational entropy increased not only in settings that are physically difficult to realize, such as Hall random setting, but also in more physically realizable pressed random setting. Thank you for listening my talk.
Thank you very much for the talk. Are there any questions, comments?
Excuse me, I have a question.
Hi.
Yes, please.
Thanks for the nice talk. And could you show me the definition of observation entropy?
Sorry.
The definition of observation entropy.
Yeah.
Yes. So, could you explain the operational meaning of observation entropy? Because here I'm confused about why do you, I mean, the logarithm is divided by the trace pi. Because as I understand, so usually the entropy is defined or a probability distribution, but here it is not. So then what's the reason and how do you explain this expression?
Okay. if remove this term, then observational entropy is Shannon observable entropy.
Yes.
This is, yeah. If this term, then we call this observational entropy. This is yeah. This term is sum of volume term of log, and this term is can be can be reformalized by sum of Shannon observable entropy plus sum of Boltzmann entropy term. Then and observational entropy is sorry, not even
Or precisely, my
sorry, I
question.
want to make comment for this interpretation. So, as you know, Polymer entropy can be write down by using the omega relative entropy when sigma equals to identity.
yeah.
Okay. So you can consider sigma equals second argument is identity and minus of relative entropy equal to Polymer entropy. So
Yeah.
now we consider measure after measuring that kind of relative entropy. So then that quantity is minus of this one.
Yeah. Yes. Observational entropy is equal to divergence of
Measure the divergence. So.
yeah, measured divergence. Yeah. This is
Let's continue the question because we know that the phenomenon entropy can have the operational interpretation in Schumann compression, right? My question is that does there exist information task or some
yeah.
task to interpret this quantity?
I don't know operational interpretation or information task.
Okay, thank you much.
Okay.
So sorry, I have another question. So I missed that. So you consider some several design or how to measure or something. So
Yeah.
when you use this kind of approximate to design or how to measure, so
Yeah.
I missed that part. So
Yeah. This one. This one.
So how random. So if
Random.
you take how random, okay, I understand. What is SP? I can't remember what is SP.
FP? Sorry.
SP.
SP is observational entropy.
Observation entropy. But I'm confused. In that case, you fixed some measurement.
Yeah.
Once you fixed some measurement, but
Yes.
this one somehow depend on the definition of measurement.
Yes.
What measurement you fixed here?
Yeah. Yes. This is fixed measurement, and then we consider for unitary sample from.
So that result does not depend on the choice of measurement.
This parameter is depend on measurement P.
Where you define this parameter?
This defined as this one,
Oh.
and we control this order. Then we conclude the concentration of observational entropy.
So anyway, you consider behavior of the observational entropy by randomly choosing that's unitary.
Yeah. Mm. Sorry.
Okay, I understand. So, many people often consider that kind of a random choice of random choice of unitary, but
Yeah.
in common setting somehow you consider big quantum system maybe endowed state, and you take that random unitary, and you take partial trace, and then you consider Von-Neumann entropy. So in that case, there are similar evaluation. This is very common analysis. But your case is slightly different. You make some measurement.
Yeah. This is depend on measurement, and if we consider coarse macro measurement, then we conclude the concentration of this concentration, or we have concentration this form. Yeah, this is deeply depends on measurements, and we should control measurements. Yeah.
Okay. Are there any other questions? If not, let's thank the speaker again. So this is the end of the workshop. On behalf of the organizers, I'd like to thank all the speakers and the participants of the workshop. A few words. We are very sorry for the cancellation of the program the first day. We did not check that historical background of September 18th. We appreciate your understanding of our decision. I think there is a long history of communication between China and Japan. For example, we have several traditional culture in common. And I think important thing is to keep a good relationship between people in Japan and in China. And yeah, we hope our activity do contribute to it. Hope to see you again in the next year. Thank you very much.
Thank you very much.
Hayashi-san, do you have anything to say?
No.
Okay. So this is the really end of the workshop. Thank you very much.
Thank you.